Hi, this is Mr. Mitchell with another video on motion. You know, we have been studying motion for a little while. Someone else that studied motion was Newton. Many years ago, Newton had a chance to do a lot of work with moving objects, and he came up with three claims about moving objects, and we call them Newton's laws of motion. So the first claim is this. The first law of motion says a body at rest tends to stay at rest, and a body at motion tends to stay in motion. So say we have this soccer ball. This soccer ball, if there were no other forces put upon it, would tend to stay there and stay there and stay there, and it would not move until there was some kind of force put upon it, whether it's a force by a human or force by some kind of animal or force by nature. It would tend to stay there. So whenever it is kicked by this human, that's the force that would make it propel, then it would be a body in motion, and that body in motion tends to keep moving until a force is put upon it. Now here on Earth we have the force of gravity that will bring it down, and we have the force of friction once it is rolling that will slow it down. But if this soccer ball were to be kicked into space somehow, then you wouldn't have as much gravity looming around. You wouldn't have the friction, the resistance that would hold it. So you would think, if this claim is correct, the soccer ball would just keep moving. And whenever you have asteroids that are in space, scientists think that that's exactly what's happening with them. They were propelled from whatever star or whatever celestial body they were originally came from, and they just keep moving in space because there is no force in which to stop them. Consider this possibility here. Let me hand this woman the Starbucks coffee. Say this woman bought some Starbucks coffee and went in the parking lot to crank up her car and sip her coffee wherever she's going. And she put the coffee on top of the car. But what if she got distracted somehow and then took off with the coffee on the top of the car? If the coffee were big enough, it would probably stay there for a little bit, and say she slammed on the brakes, what would happen to the coffee? It would go flying straight ahead, and that is one of the evidence that some people use when suggesting that this claim of Newton's is true, that this coffee was in motion whenever the car was in motion. So since it was in motion, it tended to want to stay in motion until some forces, gravity, friction, ended up stopping it. So that is Newton's first law of motion, the first claim. Here is his second law of motion. Force equals mass times acceleration. This probably needs some explaining. The force that an object has in moving is directly relational to how big it is and how fast it's accelerating. For example, here we have a bigger mass that this person is pushing. They're pushing the bigger mass, and if they use the same acceleration, say this person is using the same acceleration to push this mass and the same acceleration to push this mass, if you have the same acceleration and a bigger mass, that means you have more force. And it does make sense that this larger box would have more force to it if it is accelerated at the same rate as this box. Kind of the same thing here. Say we had a strange planet where there were wooden cars and lead cars. Give me one of those wooden cars there. If this person is pushing the wooden car and the lead car, same thing holds true. If they put the same acceleration, the lead car would have more mass to it. It would weigh more. So you would have more force with the lead car. But you kind of have a similar thing happening here. If you put the same amount of force on it, the one that has the most mass will be harder to move. Here we have two shopping carts, one that is not full and one that is full. The one that has the most force on it, if somebody's pushing it at the same rate, of course, will be the heavier one. If one is pushed toward your vehicle, I would rather it not be this one because it would be heavier and would probably cause more damage because it had more force. So Newton's second law, his second claim, is that force equals mass times acceleration. Let's go to the third law. Third law, or his third claim, is for every action there is an equal and opposite reaction. And I have once again put three figures from the internet to kind of illustrate this, and this is a pretty good one. If you blow up a balloon and then let it go, what happens to the balloon? You have air pushing out this direction, but you have an opposite reaction. You not only have air pushing out, you have the balloon that goes the other direction. So that would be an example of an opposite reaction. And Newton would claim that this reaction is equal to that reaction. Same thing if you're standing on a boat and you step off. What's going to happen to the boat? It's going to go in the opposite direction. This is the action, and in the opposite direction is a reaction. Now, keep in mind, if Newton says that for every action, you have some that are a little bit harder to imagine. For example, you have the action of somebody pushing the finger against the wall. If Newton is correct, that means that the wall, in effect, puts a force back upon the finger. It's an equal and opposite reaction, you might say. Now, something else I might also say, if you do some kind of action with your finger, sometimes your elbow ends up going in the opposite direction, kind of like if you are throwing a baseball or a softball. So what do you think about Sir Isaac Newton's claims of a law of motion, about bodies of rest and bodies in motion, about force equaling the mass times the acceleration, and for every action there's an equal and opposite reaction? What can you prove of these three, or are they provable? Hope you have some food for thought here in this video.